Hi, Megan. It's great to see you.
Hi, thank you. Good to see you as well.
Now, today it's early March. You had told me about the volunteer work that you do at an elementary school chemistry club. And I know that involved Valentine's Day, an experiment we wanted to talk about, which we'll get into. But did doing paper chromatography with those students change the way you think about introductory separation science at all?
Beforehand, I had not thought about teaching separation science or chromatography to such young students. So that was certainly something I had to do beforehand was try to use words that were more approachable for them. So I was looking for what's a different word for affinity, attraction. But it's a humbling reminder that science is really magic to young children, especially when they're seeing something for the first time. And so, watching colors of dye separate on chromatography paper, they weren't thinking about partition coefficients or stationary phases. They were just watching something change. Something invisible becoming visible is a concept that children that young can understand, and they can particularly understand a before and after. So, yeah, I was just explaining to them that this is essentially what I do with more complicated equipment.
At the American Society for Mass Spec conference last year, I watched a presentation where they did a separation with Kool-Aid. And as a 36-year-old at the time, I was even blown away by just how instructive I thought it was for people who are just learning about, let's say, columns for the first time and just how basic separations work.
Hmm.
So, if you had to explain what's being done with the Mars simulation chamber to those fifth grade students and using the chromatography experiment you did with them as an analogy, how would you begin to explain that to them?
Yeah, so I think I would first begin by um, maybe bypassing some of the experiment and saying, I'm creating a mixture in the Mars simulation chamber, the same way that we had mixtures with the dots of dye. So, say, remember we put the dot of ink on the chromatography paper, we watched it separate into all of these different colors because different compounds move at different speeds. So, yeah, I use the Mars simulation chamber to create a mixture like that. And my samples, they start as one chemical, but then I blast them with fake Mars sunshine and some salts, and they then separate into lots of different molecules. We saw the colors separating into different components, and we can then pick out yellow, green, red. I also separate a large sample into a lot of different components so that I can then analyze them individually. So it's easier for me to see as well when the compounds are separated. That being said, all of my compounds are invisible, but I have to use expensive machinery to see them.
No, that makes a lot of sense. And a lot of us think of chromatography as a way to identify what's there, but your work is really about identifying what's left behind after degradation. How does that change the way you approach analytical method development?
Yeah, so it is complicated. And that's a really good question because normally you're looking for something specific, you have a standard to run it against. You can tune your methods to find that needle in a haystack. But I don't actually know what these degradation products are ahead of time. The biomolecules can fragment into hundreds of things, and many of them are suspected to have never been seen before because we've never done this kind of chemistry in a Martian environment. So, I can't just target the known compounds. I have to cast a wider net, and I use, multiple instruments, GCMS, LCMS, IC, NMR. And honestly, like I run my samples with multiple analysis methods on the same instrument. Maybe one that's designed for lipid detection, one that's specifically for oxidized sterols. I have a super long, just default method that's anything I haven't found yet. So, yeah, it's more like an exploration than being able to hunt for single molecules. And basically, it's instead of like a needle in a haystack, I'm trying to figure out what the haystack looks like after Mars is finished with it.
And in terms of what the Curiosity rover has detected, chlorinated hydrocarbons and aromatics like chloromethane and chlorobenzene were detected in Martian mudstone. Why did those detections raise questions about whether we're seeing indigenous organics versus analytical artifacts?
So here's the thing, like the GCMS, the Viking landers arguably discovered the first indigenous Martian organics, but they were kind of discounted as being contaminants from the terrestrial environment. But it has the GCMS, the Viking rovers did, and the Curiosity, the sample analysis at Mars instrument, has a GCMS. The thing is these are both pyrolysis GCMS. So they heat the sample up to 1,000 degrees to volatilize it and then analyze the samples. And when you heat organics in the presence of oxychlorine salts, you get destruction. Like we use oxychlorines to clean here on Earth. Basically, since the Martian soil is full of these oxychlorine salts, and we have to heat them up to get an analysis, it's basically asking, are these Martian organics that were chlorinated in the oven during the GCMS analysis? Are they terrestrial contaminants, again, chlorinated in the oven on Mars during the analysis? Or the third option is that they could be indigenous chlorinated compounds. And what if the chlorination happened naturally on Mars over billions of years of UV irradiation in the presence of oxychlorines? So, yeah, that's basically the last option, is what my research focuses on. It's like, did Mars do the chlorinating, or did we do it in the oven on Mars? And I'm just testing whether Mars has done it first.
That's a really great explanation.
Thanks.
That makes a lot of sense. Just in general terms, based on your experience having to talk about this work a lot, I'm sure, what are some of the biggest misconceptions
Yeah.
people have about finding organics on Mars?
So I have two, kind of. The first one is that to a lot of people, especially the general public, organic means life. And that's just not true on the face of it, because we have a lot of molecules that contain carbon that are abiotic processes. So carbon is everywhere in the universe. We've got it in meteorites, on comets, even in just interstellar dust clouds. We've found organics on the grains. So we know that there are organics on Mars because there have to be. They're showered in from interstellar space. But that doesn't necessarily mean life. And so conflating those two, oh, Curiosity found organics on Mars, it doesn't always mean what people might think it means. And the second one, I think, is more aimed toward the astronomy and I guess astrobiological community. And that's that basically Mars is cold and dead. But It really isn't. There's still lots of geological processes at play there. And people fail to realize that Mars is our closest sister in the solar system, coalesced from all the same materials that the Earth did, and had a water cycle, was considered habitable for an evolutionarily significant timescale. So I think that people just brush Mars off as, not as interesting. But with these geological processes, like, we have the capacity to unearth or unmars, if you will, our history of past life on the planet. All of that could be down deep in the soil, and we just haven't gotten there yet. So,
No, absolutely. And in your research, you mentioned using a toluene BHT extraction solvent system. What role is BHT playing in that workflow?
yeah. So BHT, butylated hydroxytoluene. So it's an antioxidant, the same things that we put it in, we put it in food to keep it from going rancid. And that's similar to how I use it. Also, an antioxidant. I'm studying oxidation that happens in the Mars chamber. I don't want any oxidation to be happening outside during the analysis, during the extraction. So basically, it's just an oxygen molecule scavenger. It acts as a sacrificial antioxidant to keep excess oxygen off of what I actually want to measure.
And speaking of oxidation, after your liquid-liquid extraction, you analyze aqueous fraction with the LCMS for polar products. So, what kinds of oxidation products are you expecting to see partition into that phase, let's say?
Yeah, well, I do a lot of work with sterols, cholesterol in particular. And when it oxidizes, you're adding oxygen molecules in the form of hydroxyl groups, ketones, epoxides. So these oxygen molecules, they do make the molecule more polar overall. And so, yeah, while the cholesterol is going to hang out in the organic layer, hopefully I will be getting some products into that aqueous layer that wouldn't necessarily be soluble or analyzable.
I'll say that I think your work is just super interesting in general. From the context of this podcast, it's also very cool when we're able to discuss a lot of the common approaches all as part of one research presentation or paper. And by that, I mean, like you noted, LCMS, GCMS, NMR. This is all what we really focus on discussing with researchers. So it's so cool. One of the most interesting parts of the workflow was using ion chromatography to confirm that the residual salt content is below the level of detection before running GCMS. How catastrophic would it be for the GC system if those salts made it all the way through?
Well, it can get pretty ugly. Um, Salts in a GC system, kind of like sand in a car engine. Like, it just has nowhere to go, and they kind of sit, accumulate, clog up the column, and mostly, they contaminate the front end of the column where I expect a lot of the smaller, most volatile compounds to elute. So, of course, that makes identification very difficult. And the kicker is that my samples are full of salts by design. And I then go on to derivatize, which involves heating my sample up. And if there were leftover salts, then I'm doing exactly what I'm trying not to do, which is heat up my organics in the presence of perchlorate. So essentially, it's important for my own research that I'm not accidentally working with perchlorate at a high temperature, but also, if there are salts that get into the column, I'm ruining it for everybody else. So, yeah, the ion chromatography is just an insurance policy, if you will.
Yeah, that's a great way to explain it. Speaking of the derivatization, what kinds of functional groups are you trying to stabilize to make more volatile at that point?
In general, the like major analyte, like cholesterol, has a hydroxyl group, so it's not going to move through the column very well underivatized. And that's similar to, I think, a lot of the sterols and oxidized products, is that you get hydroxyl groups and carboxyl groups and a lot of like long chain acids. So the problem is those groups form hydrogen bonds. It makes them kind of sticky and hard to vaporize. So yeah, you need to be able to get them more volatile, and you can do that by derivatizing them with BSTFA, actually, is what I use, and replacing those hydrogens for bulkier TMS groups. Then, it helps the molecules flow through cleanly, gives me nice sharp peaks after derivatization.
Sharp peaks, that's what we like
Right?
to
That
hear.
Gaussian distribution.
One thing I picked up on, it sounded like you were especially interested in minimizing sources of GC column contamination. What are the most common contamination sources that you feel like you're fighting against?
Yeah. So, being a frequent user of GCMS, I feel like I had to become an expert on contamination just because, like, my first couple of years of my PhD, I was just like, I have no idea what these compounds could be. So, basically, I think, three big groups of contaminants. One, the salts. Of course, you don't ever want to put salt through your column. You don't ever want to put water through your column if it's, the wrong stationary phase. But basically, the second one, GCMS consumables. So inlet, liner, even just like the needle can become too dirty. You have the septa, just like frequently replacing a lot of those consumables can seriously clean up the baseline and contaminant peaks. The third is like siloxanes from plasticizers, from just kind of normal things that we use in the lab. So vial caps that aren't PTFE lined, or everybody has the plastic pipette tips, the micro pipettes, and those can also leach plastics. So essentially, for me, my entire bench is glass and metal. So I have all glass micropipettes, all glass vials, filters. I silenize it all myself to make sure I get the most complete recovery. And then also just common lab detergents and soaps that are used for glassware. They are a huge source of contamination. So I actually don't use any detergent when I clean my glassware. Everything is just a system of solvents and nitric acid and yada yada, and then high heat baking to clean all my glassware, just because like detergent has been a really, really bad contaminant. So, yeah.
I'm surprised that hasn't come up previously with what your findings have been about
Well,
how much of a contaminant it can be.
I know I've done so many different chromatography trainings, and in all of them they make a note like not to use plastic like pipette tips, but nobody follows that. Like in your lab, that's just the most convenient go-to. But yeah, it's like all of the technical manuals tell you not to do it.
Yeah, one of Organimation's blow down evaporator options, instead of using the stainless steel needles, which is how we typically deliver the nitrogen gas. We have the pasture pipette adapters, but people are primarily using glass. My thinking had always been that there's just this big battle between convenience and sustainability when it comes to the glass versus plastic battle, let's say.
Yes. Yeah. And I do fight that pretty often because I care about the environment and all the waste that happens in chemistry labs. Like it's unavoidable, but it's painful. So, yeah, I know that I spend a lot of my time washing glassware so that I'm not using like single-use vials. But I think for me it's a worthy trade-off.
Yeah. How does working with high salt environmental matrices on Earth prepare us for extraterrestrial sample analysis?
So, are you asking like high salt earth analogs like the Atacama Desert or dry valleys in Antarctica? Or are you asking like how my research matrices kind of transfer to Mars?
Honestly, both. I suppose the thinking would be it's really easy in a sense to focus on some of the unique challenges you face, but I'm sure you've been able to apply so much you've learned just doing environmental matricy work during your undergraduate and graduate work. I'm sure you've applied a lot of lessons that have helped you with more unique and yeah, extraterrestrial samples as well.
Other people in our lab do research on places like Atacama desert soil and Antarctica dry valleys. And studying Earth's most extreme environments, where this is where life fights but still thrives, those harsh environments on Earth are the closest terrestrial analog we can get to Mars. So we definitely use those samples from those places to analyze and kind of look for the tiny organics and how to find them in a sea of salt interference. The extraction challenges are similar, the salt removal, similar. So, yeah, those matrices that are born of the more harsh environments on Earth, they are capable of harboring life. So, they hopefully serve as a good analog for Mars. The whole idea is that these techniques that we're refining now, like the ion chromatography cleanup step I mentioned, those are directly transferable to Mars sample return if it ever happens. So basically, we're practicing now with low risk samples on Earth so that if we get these beautiful little samples from Mars, we'll already have processes and frameworks to analyze them. So.
And how do you balance sensitivity versus column lifetime when you're chasing extremely low abundance degradation products?
Yeah, so I know that that's like a tightrope that you have to walk in industry a lot, but I am very fortunate in that I don't have to worry about it a ton just because I think a lot of those industrial GCs that you have to worry a lot about, maintenance, they're working all the time. Whereas I think maybe 50 samples a week, 50 runs a week is maybe the max that we get on our GC. So I don't have to worry a lot about column lifetime because I'm mostly concerned with like the data. So it does mean that like I heat my column up pretty high to a pretty high temperature. I push the system, I inject hot, inject concentrated samples, run it on splitless. Like I can kind of abuse our GCMS just because I'm the only one using it right now. But also, like, there have been times where we have to chop off a foot or two from the front of the column. And in GCMS, like, unlike LCMS, like, that's possible and it's not going to mess with my system too much. So, yeah, I think the real answer is, method development is what's going to help you balance those. Clean injections, like all the sample cleanup methods we've been talking about, those are all going to help so that I don't actually push the system to the breaking point. But yeah, fortunately, I don't have to worry too much because I'm a PhD student. I won't be around too much longer anyway.
I think we've done a great job covering your workflow and introducing this research at a basic level. But Megan, I'd love to hear from you if there's anything we've missed that you'd really like to share about your research, anything else people should know and take away from this conversation.
There's really a war on science right now, and it's hard to kind of push through all the red tape and still be involved in the scientific community and, push for these more existential questions. I really think that things like looking for life outside of Earth are valid scientific endeavors. I think that if we find just one more example of life emerging somewhere else in the universe, then the possibilities for life in the universe are pretty endless at that point. So, yeah, I guess my main message is this research is important and we should all continue to look up.
Absolutely. Well, Megan, I really appreciate the time today. Thanks so much for sharing your work with the audience.
Of course, thank you for having me. It's great to be able to talk to an interested person.